In fact, the most dangerous places in the universe may not be black holes, but those regions that are too clean, too quiet, where nothing exists at all. Imagine such a region. Its volume is so vast that even light, traveling at 300,000 kilometers per second, would need hundreds of millions of years to cross it. Even the Milky Way, the galaxy we inhabit, appears pitifully small in comparison. And within this space, there is almost no matter at all. Compared with other parts of the universe, it is like an immense desert. There is not a trace of starlight within it, only vast, unbroken darkness. This may sound like the fantasy of a science fiction novel, but it truly exists in the universe we inhabit. It is called a cosmic void. And beyond that, there are even supervoids. In this episode, let me take everyone watching on a journey back several hundred years, to see how humanity first discovered them. At the end of the 18th century, with the invention and improvement of telescopes, humanity began to truly move beyond the limitations of naked eye observation, and step into the dawn of modern astronomy. For the first time, astronomers were able to map the structure of the Milky Way, with relative accuracy, and sketch a rough picture of the distribution of stars. In that era, scientists could scarcely imagine that beyond our own galaxy there existed a vast universe, let alone that on cosmic scales there could be such enormous empty regions. At the time, humanity's understanding of the universe was focused more on scattered points of light, rather than the complex structures we see today. Entering the 20th century, telescopic observation capabilities advanced rapidly. With the development of radio astronomy, optical imaging, and spectroscopy, humans gradually realized that the Milky Way is merely a speck of dust in the cosmos. Beyond our galaxy lie hundreds of millions of other galaxies, distributed throughout the boundless universe. As statistical studies of galaxy distributions progressed, scientists discovered a puzzling phenomenon. In certain regions, the number of galaxies was significantly lower than expected. These empty areas were initially thought to be observational errors, or the result of insufficient instrument sensitivity. However, as observational techniques continued to improve and evidence accumulated, these low-density regions were repeatedly verified and confirmed, eventually receiving a unified name: cosmic voids. What truly brought cosmic voids into the scientific spotlight were the redshift surveys of the 1970s and 1980s. Redshift is a key method for measuring galactic distances. It uses the shift of absorption lines in spectra to determine how fast galaxies are moving away from us. By observing tens of thousands of galaxies, astronomers constructed three-dimensional maps of the universe. These results revealed a startling fact: galaxies are not randomly distributed, but instead cluster along vast filamentary structures, forming an enormous web-like pattern. This phenomenon is known as the cosmic web, and between the strands of this web lie vast, empty regions. These are the cosmic voids. This discovery overturned humanity's assumptions about cosmic uniformity. Traditional cosmological principles assumed that, on sufficiently large scales, the universe should appear roughly the same in all directions. But the existence of cosmic voids reminds us that the universe is far more complex than we once imagined. Entering the 21st century, large-scale observational projects, such as the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey, have drawn far more detailed maps of the universe. These projects recorded the distribution of millions of galaxies, precisely revealing the sizes, shapes, and locations of voids. With these data, the full picture of cosmic voids finally emerged. From vague speculation to scientific confirmation, this journey took several centuries. After understanding how they were discovered, let us now look at several famous voids confirmed so far. These vast cosmic deserts are so enormous that they inspire awe in anyone who contemplates them. In 1981, American astronomer Robert Kirshner and his team, while studying galaxy distributions, unexpectedly discovered a region that was almost completely empty. This was the cosmic void later known as the Boötes Void. The Boötes Void has a diameter of about 330 million light-years, and is regarded as one of the largest voids in the universe. Based on the average density of galaxy distribution, this region should theoretically contain more than 10,000 galaxies, yet observations have revealed only about 60. This contrast is like finding a barren desert in the middle of a dense forest, strikingly out of place. Even more mysterious is that the few galaxies inside the void are not randomly distributed, but arranged in strange tubular or chain-like patterns. This anomalous feature has yet to be reasonably explained. The Boötes Void is therefore known as a cosmic desert. Its existence even challenges cosmological principles, because on such large scales, we should observe uniformity. Yet the Boötes Void breaks this assumption. After the Boötes Void, scientists discovered another astonishing void in the direction of Boötes' neighboring region. This area is known as the Boötes Supervoid. Its scale far exceeds that of ordinary giant voids. and is one of the largest cosmic structures ever discovered by humanity. The Boötes Supervoid spans nearly 1 billion light-years. In other words, even light would need a billion years to traverse it. Although its emptiness is not as extreme as that of the Boötes Void, its enormous volume grants it a unique position in cosmological research. What draws even greater attention is that the Boötes Supervoid appears to be linked to an anomaly in cosmology, the cold spot in the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, and is generally distributed uniformly. Yet in the direction of Boötes, there exists a region that is noticeably colder than its surroundings. Scientists speculate that this cold spot may be caused by the supervoid. When photons pass through a supervoid, they lose energy due to the Sachs-Wolf effect during gravitational lensing, resulting in a temperature anomaly. In addition to Boötes and Boötes' neighboring regions, humans have also discovered another equally astonishing void, in the direction of Cain's Venatici, known as the KBC supervoid. Its diameter reaches as much as 1.2 billion light-years. In the three-dimensional structure of the cosmic web, it resembles a lurking beast of the void. Although humanity has mapped increasingly detailed distributions of cosmic voids, one fundamental question continues to trouble the scientific community. How did such enormous voids form? To understand this, we must return to the birth of the universe and its early stages of evolution. Scientists have proposed multiple theories to explain the formation mechanisms of voids. Each carries some evidence and rationality, yet all still face unresolved problems. Cosmic inflation is currently one of the most widely accepted theories. According to this theory, less than a second after the Big Bang, space underwent an extremely rapid expansion. During this very brief period, the volume of the universe grew exponentially. Quantum fluctuations on microscopic scales were stretched to cosmic dimensions. These early quantum fluctuations served as seeds in subsequent evolution. In some regions, matter density was slightly higher, so matter gradually gathered under gravity to form galaxies and galaxy clusters. In other regions, matter density was slightly lower. Over time, these sparse regions were further amplified, eventually evolving into the cosmic voids we observe today. The strength of this theory lies in the fact that it not only explains the origin of voids, but also simultaneously explains the formation logic of the cosmic web. Its weakness, however, is that at present, we still cannot directly detect the inflationary process itself, and can only infer it indirectly, through subtle fluctuations in the cosmic microwave background. Another explanation emphasizes the role of dark energy. Dark energy is a mysterious force that drives the accelerated expansion of the universe as a whole. Scientists speculate that, over the long course of cosmic evolution, dark energy may push galaxies out of low-density regions, and draw them toward areas where matter is more concentrated. As time passes, matter within voids continues to decrease, while surrounding matter becomes increasingly concentrated. The result is that low-density regions are gradually stretched outward, eventually forming the enormous voids we see today. This theory neatly explains why voids continue to grow. Observations also show that the average size of voids increases with the age of the universe, consistent with the driving influence of dark energy. A third hypothesis suggests that the formation of cosmic voids is actually a byproduct of the natural evolution of large-scale cosmic structures. Just as gaps automatically form between bubbles when bread ferments, galaxies and galaxy clusters gradually aggregate under gravity, and the remaining empty regions naturally evolve into cosmic voids. Under this explanation, voids are not independently created, but are secondary spaces formed during the construction of the cosmic web. In other words, voids are not made, they are what is left behind. There are also more speculative hypotheses that link voids to anomalies in the fabric of spacetime itself. According to topological defect theories, the universe may have retained certain irregular flaws during inflation. The spacetime structure in these regions differs from their surroundings, preventing matter from easily accumulating there. These spacetime fissures were gradually amplified during later evolution, ultimately manifesting as large-scale voids. Although this theory lacks direct evidence, it possesses a degree of plausibility in mathematical and physical models, offering an alternative way to explain extreme voids. Some scientists have also proposed that cosmic voids may be related to primordial black holes. These are thought to have formed from extreme density fluctuations in the early universe, rather than from stellar collapse. If such primordial black holes were abundant, their gravity might have cleared surrounding regions of matter, thus giving rise to voids. On the other hand, dark matter may also be a key factor. Although invisible, dark matter accounts for about 85% of the universe's total matter content. It weaves invisible filaments of dark matter that dominate the distribution of galaxies. If these filaments collapse or are absent for some reason, They would leave vast vacuum regions in the universe. Though each of these hypotheses has its shortcomings, they all point to the same core idea. Cosmic voids are not accidental products, but profound imprints left by the early evolution of the universe. Despite the large amount of observational data we have accumulated, research on cosmic voids remains extremely challenging. The sheer scale of the universe itself is a major obstacle. To study voids, we must analyze galaxy distributions across billions of light-years, requiring enormous sample sizes and high-precision observations. Even the most advanced telescopes today can observe only a limited portion of galaxies. Dark matter and dark energy are two unavoidable mysteries in void research. They dominate the universe's large-scale structure, yet no one has been able to directly detect their true nature. This forces scientists to rely on mathematical models and indirect observations, making it difficult to reach definitive conclusions. Computer simulations play a vital role in cosmological research, yet even the most complex simulations struggle to fully reproduce the scale and properties of cosmic voids. Some simulation results differ from observational data, suggesting that our current theoretical framework may still be incomplete. Fortunately, scientists have not stopped. Projects such as the Sloan Digital Sky Survey and Dark Energy Surveys have already mapped galaxy distributions spanning hundreds of millions of light-years. Meanwhile, supercomputer simulations are steadily approaching the complexity of the real universe. For example, simulations involving tens of billions of particles can now reproduce the basic form of the cosmic web, allowing us to create voids in virtual universes and compare them with observations. These efforts continue to narrow the gap between theory and reality. So why do we study cosmic voids? How do they help advance science and technology? Voids provide natural laboratories for studying dark matter and dark energy. The motion of galaxies inside voids, and the way light propagates through them, can indirectly reveal the properties of these two mysterious components. In other words, voids are key clues to understanding the universe's invisible scaffolding. The size, distribution, and morphology of voids can serve as touchstones for testing cosmological models. If a model can accurately predict the properties of voids, it is likely closer to the truth of the universe. If predictions sharply contradict observations, the model must be revised or even overturned. This makes cosmic voids a powerful driver of progress in physics. The existence of cosmic voids also reminds us of the profound connection between quantum physics and cosmology. Early quantum fluctuations may have been amplified into the macroscopic voids we observe today. This fact itself is evidence of the deep intertwining of the microscopic and macroscopic worlds. Beyond scientific research, cosmic voids have inspired many more imaginative hypotheses. Some theorists propose that cosmic voids may not be entirely empty, but could be interfaces leading to parallel universes. According to string theory and multiverse hypotheses, in addition to the four-dimensional spacetime we inhabit, other dimensions and universes may exist. If this idea holds true, voids would be like membranes at the edge of the universe, possibly connecting to entirely different physical worlds beyond. Of course, this view remains largely speculative, but it offers a romantically imaginative perspective on our understanding of the universe. Another viewpoint is more closely tied to physical reality. Cosmic voids may be direct relics of early quantum fluctuations. Energy fluctuations in the microscopic world were amplified by cosmic inflation, eventually manifesting as macroscopic voids tens of billions of years later. This means that every void is a fossil left behind at the birth of the universe. When we gaze up at the night sky, we see shimmering stars, but behind this sea of light lie far greater silent presences, cosmic voids. They emit no light, yet shape the grand structure of the universe through emptiness itself. Scientists call them the silent guardians of the cosmos. They record the earliest traces of cosmic evolution, bear witness to the power of dark matter and dark energy, and may even be the key to understanding parallel universes. Humanity's exploration of cosmic voids is far from over. Each new observation and theory brings us closer to the truth. Perhaps one day, we will truly uncover the secrets of these immense voids. But until then, they will continue to exist silently in the vast universe, gazing upon billions of stars, and guarding the ultimate mysteries of the cosmos.